One less sponsor. When will we finally have a useful quantum computer capable of solving real-world problems? According to Microsoft, in a matter of just a few years, a couple of months ago, they dropped a bombshell. They unveiled Majorana 1,
a topological core. And since then, researchers have been looking for a very specific, very useful quasi-particle within it, the Majorana particle. Last year, we were able to observe it for the first time. And this year, we're able to control it.
the first chip based on topological qubits, according to them, that is. Because I don't think they have a topological quantum computer. This was more marketing than science. To date, nobody has detected a Majorana mode, neither have they, or at least they haven't proved it. Let's discuss the real physics behind all of this. What are topological qubits? Why would they be so revolutionary? What are exactly these Majoranas? And what is it that has raised many eyebrows among experts? It's the greatest scientific challenge of our time. Big multinationals, startups, and research groups are all after it, and every now and then, a revolutionary chip or a new milestone is announced. It seems that the topological quantum computer is one of them, but before carefully explaining all of this, let's start with the basics. What is a quantum computer and why so much hype? I'm sure you have heard it 1,000 times. Ordinary computers, or your cell phone, or your TV set, or your Tamagotchi, process information using bits, zeros and ones. Zeros and ones. The key to quantum computers is they don't work like that. They are not better computers, but different computers. Instead of normal bits, they use quantum bits, qubits. They can not only be 0 or 1, but exist in countless mixtures of both states, in a quantum superposition, 0 and 1 at the same time. And this feature forces us to rethink everything from scratch. Off with operating systems, off with all the hardware we have, off with programming languages. Dumb cutie, you can stay. At the end of the day, this is a whole new way of computing, quantum computing. But why would we want something like this? Why put money into it and not, for instance, into treats with 3 states? The more the better. The point is that quantum computers would be ideally suited to simulate situations involving quantum systems, problems that not even the most powerful supercomputers can solve in a reasonable amount of time. It seems pretty obvious. If we want to study a phenomenon governed by the rules of quantum mechanics, the best we can do is use a computer that obeys those same rules. That would be great for science, especially in chemistry, biology, or material science, where presently we can only perform calculations involving molecules with a few atoms, at the very best. As a brief aside, I have even read that quantum computers will serve to stop climate change and to eradicate cancer. Let's see, will they be useful to better understand huge biomolecules that, after lots and lots of tests, would end up in drugs that, after many exasperating trials, could help fight certain types of cancer? Well, let's hope so, but it is not so straightforward. But, of course, if big tech companies are involved in this, it's not just because they love science, but also because, you know what I mean. The great promise of quantum computers, and let me repeat this so it's completely clear, promise is that they will outperform classical computers also in other tasks. This is a rather incorrect analogy. If we are ingenious enough, a quantum computer could work as if we had several classical computers in a superposition, combining their processing power to perform the same task. Now, programming a quantum computer to work that way and then getting a result out of it, that's a huge problem. There are many theories around the world designing these quantum algorithms. We already know some that will kill it, provided we can solve a lot of technical problems connected with them. That's why I insist on the promise part. But back to practicalities. Building such a quantum computer, what about that? To implement a qubit, we need some kind of system that has 2 different states and can exist in a superposition. Just like we use transistors to represent bits, we need a quantum entity in order to create are qubits. There are many different proposals. We could use the spin of an electron, the two polarizations of a photon, two energy levels of a trapped atom or an ion, and even defects in diamonds. Probably the most popular approach, the one explored by large companies such as Google or IBM, is using qubits based on superconducting materials, as we explained in this other video. The biggest challenge in building quantum computers is that quantum superposition happens to be extremely fragile. Any kind of interaction with the environment can change the state of a qubit, causing it to collapse into 0 or 1. Quantum effects disappear, and we are left with a normal bits at a premium price. To prevent this from happening, or at least delay it as much as possible so that we have time to perform our calculations, we must isolate our chip from any kind of noise, such as external radiation or even thermal vibrations of the particles making up the chip. And that's the reason why quantum computers are always placed inside several vacuum chambers, so that not a single molecule of air can disturb the state of the qubits. In addition, they are kept at temperatures close to absolute zero, to almost completely suppress the vibrations of atoms. Even then, it is impossible to eliminate all the noise, and this leads quantum computers to make many errors. Of course, it is possible to correct them, but it is very costly. Here is the idea. Imagine that the value of your normal bits changes from time to time, screwing up your computation. How can you detect and correct such an error? One possibility is to take a bunch of bits and have them do the very same thing, the same process inside the computer. Then you just have to look at the whole. If one bit disagrees with the others, you will know there is an error, and the true value is the global one. Surely, all the bits won't have an error at the same time. If errors are frequent, you will need more bits to pick out the true results. And something similar happens with qubits. Tens, hundreds, or even thousands of physical qubits must be used to implement a single logical qubit, the one that goes into the calculations. And that is the major obstacle to scaling up quantum computers to a size where they could be really useful. In order to do so, we would surely need hundreds of thousands or even millions of physical qubits, while the current record is just over 1,000. But there is an alternative. We could use a system where noise protection comes as a standard, built into the hardware itself, so to speak. This is the idea behind topological qubits, and as we are about to see, it's all based on splitting an electron in two. Wait, what do you mean splitting an electron in two? Electrons are fundamental particles which cannot be divided into simpler ones. The thing is, mathematically, you can think that an electron is made up of two particles, two Majoranas, a hypothetical type of particle theorized around 100 years ago by a brilliant Italian physicist, Ettore Majorana. Microsoft's press release gives the impression that they found a new elementary particle, first CERN with the Higgs boson, and now them. But that's not the case, it's more complicated. We are not talking about particles, but quasi-particles. I'll give you an example. Imagine that we have a lattice of atoms and one of them is missing an electron. This can trigger a cascade of movements. Another electron jumps there, leaving behind an empty space that is immediately occupied by yet another electron, and so on. Instead of saying that all the electrons are moving, let's focus on the whole. It also looks like a moving particle. If we take this idea seriously, such a particle must have positive charge. There's no choice. If I take an electron away from the system, a hole appears, but I have also taken with me the electron's negative charge. Therefore, the hole is positively charged. In fact, it is kind of an anti-electron, as they annihilate each other. Of course, holes are not actual particles. What is real is this ensemble of electrons that has an empty state. What's happening is that all those electrons as a whole interacting with each other do behave like an individual whole. This is an example of a quasi-particle. Could it be that something similar happens in our case? That there is a system in which the collective behavior of electrons makes them appear as they were composed of two particles, in which there seem to be Majorana particles? And more importantly, what good would that do? The thing began to take shape in 2000. That year, Alexei Kitaev noticed something rather curious. Imagine that we have a row of electrons. Now, a bit of imagination. Let's think that each one is formed by a pair of Majoranas. Seen this way, we can have the Majoranas paired like this, or break up this pair and connect them in this fashion. At the ends, there are two Majoranas left alone. Let me insist, this does not mean that there is half an electron at each end. All the electrons of the chain are playing a part. Because of the characteristics of the systems in which we have put them, they are behaving as if they were made by pairs of particles, as if we have left two of those isolated at the ends. Okay? Well, imagine we could empty the chain of its electrons while keeping their states, the sites where they might be located, or rather, where their Majoranas might be located. Now, let's put some electrons in. If we induce a special kind of superconductivity in the chain, we can alter the way in which the Majoranas pair up, so that we are left with those two free seats at the ends. Now, it could happen that an electron gets in the system and it splits in two, with its Majoranas going to those two ends. Whenever that happens, whenever those seats are taken, we say that the Majorana modes are occupied. If this has not occurred, we say they are empty. Occupied, empty, taken, free, 0, 1. You see where this is going. And note that we can go from one state to the other by just adding an electron. So one of the states has an even number of electrons and the other one has an odd number. And incredible as it may seem, there are ways to measure this to find out if your system is at 0 or 1. And as long as you don't measure quantum physics, those seats can be occupied and empty simultaneously. We have a potential qubit. All this Kitaev chain stuff is nothing more than a toy model and an unrealistic abstraction. In fact, the electrons here do not even have a spin. But scientists are trying to realize it in the lab by using very thin semiconductor wires, a few nanometers in diameter. It is an extremely complicated experimental setup, which requires superconducting materials, magnetic fields, and very precise conditions. But in principle, provided we manage to control everything, we could recreate these Majoranas at the ends of the nanowire. Unfortunately, we have not yet succeeded. At least, and here is the point of this video, no one has yet conclusively demonstrated the existence of these Majorana quasiparticles, even though there have been countless attempts since 2012. The difficulty lies not only in creating the Majoranas, but also in detecting them, for they are very discrete. They have no electric charge, they don't even have energy. That's why they are called Majorana zero modes. And although in principle we can use electrical measurements, there is a whole range of other much less interesting quasiparticles that produce similar signals. It is hard to know which of them we are creating. Now, detecting Majorana modes would be great because the qubits we could build with them would not be regular ones. They would be topological qubits. Oh, topology. The donut that becomes a cup, the cup that becomes a donut. We science popularizers have repeated this ad nauseam, and yet I have the feeling that this time it will help. Imagine you want to compute with donuts. You are going to look at their height to create your bits. Flatten 0, elongated 1. You modify them and let's compute. Of course, this is a risky business. Donut can fall off, get hit, and become distorted in the process. Their shape is sensitive to errors. We have chosen a very delicate property to implement our zeros and ones, but what if instead of the height, we use the number of holes? 1 for one hole, 0 for none. Now it gets better. Donuts can deform as much as you want. If there was a hole, there will still be a hole. And if there wasn't one, there still won't be one. We'd have to do something pretty bad to the donut, like break it or puncture it, for that to change. That is because the presence or absence of a hole is a global property of the system, unaffected by the little bump I have given it around here. In other words, I have chosen a topological property, and so I have an awesome and with very few errors topological bit. Something similar happens with the Kitaev chain. Our donut holes are the Majorana modes, since it is very difficult for any kind of noise to disrupt them. Two reasons. First, you cannot remove only one of the two Majoranas. That would be like leaving only half an electron, which is not physically possible. And since they are at the ends of the wire, far apart, it is very difficult for a perturbation to alter both at the same time. This is another way to understand it. We have seen that we can distinguish between 0 and 1 because the second state has one more electron. So the state of our qubit does not depend on any particular electron, but on global information about the system, specifically on whether it has an even or odd number of electrons. And that makes it much more robust to external perturbations. This is how, in theory, you wouldn't need to create redundancy. Your qubits are already rock solid, while your competitors need hundreds of qubits to, effectively, have 10 that works as expected. With 10, you already have 10. Even though, well, reality always has its way. Although it seems that you don't have to worry about certain types of errors, you now have to keep an eye on the Majorana zero modes. They are very fragile, and your system has to be able to keep generating them. You cannot get rid of the ultra-low temperatures and vacuum chambers. Microsoft claims to have created a chip with 8 of those topological qubits, and the resistance to noise opens the way to developing systems with up to 1 million qubits. And that's something. Then we will be talking about really useful quantum computers. Okay then, so why are some experts questioning the finding? Why am I so upset with the people at Microsoft? Time for some gossip. First, they made the announcement on the very same day that one of their articles appeared in Nature, one of the most prestigious scientific journals in the world. It just makes sense, you might think. They publish a paper and share its groundbreaking results. The problem is they claim things that are not found in the paper, where they do not demonstrate the existence of topological qubits, Majorana zero modes, or anything like that. They simply present a method to measure the states of such qubits in case they exist. To top it all off, there is some doubt as to whether the test they use to try to detect Majorana modes is really effective or could be fooled by those much less interesting quasi-particles that lack topological protection. I'm truly sorry, but I need to be harsh, because I think very few people have been. If you announce with great fanfare that you have a topological quantum computer that works with Majoranas when you have not even demonstrated the existence of these modes, then you are fooling us. It's just a load of hot air, and most journalists and popularizers have bought into it. In fact, the journal editors have been extra cautious. They published the report by the expert who reviewed the article. And at the beginning, it is explicitly stated that the results of the manuscript do not represent evidence for the existence of Majorana zero modes. Such a warning is very unusual. Why is Nature being so careful? It turns out that this is not the first time they have been sold a Majorana in a poke. In 2019, Microsoft opened a quantum computing lab at the Delft University of Technology in the Netherlands, headed by a leading researcher in the field. In 2012, he had published a paper announcing the detections of Majorana zero modes, although the results were not completely conclusive and were later shown to admit other interpretations. In 2018, already in Microsoft payroll, he presented even stronger evidence of their existence. But as it turns out, that last article was retracted in 2021 because of serious problems. It seems some of the scientists did a bit of cherry picking. Although they didn't act in bad faith, their enthusiasm led them to select the data that supported their conclusions, while discarding other data that could have undermined them. Since then, a second article by the same group has been retracted, another one corrected, and in a fourth one, 2 authors have withdrawn their name. Oops. And even though the particular researcher no longer works for Microsoft, one cannot help but be a little worried. The people at Microsoft claim that the results supporting what is said in the video have arrived too late. Those results were obtained while the Nature article was under review, and this is why they couldn't be included in the manuscript. And they promised that they will give further details in a scientific meeting to be held in mid-March. In a few words, the dog ate my qubits. I waited patiently to see what they would say, and no Majoranas. They show some measurements of a qubit that did not look topological at all, and which was nothing to shout about either. All these failures underline two things. Point number one, the unbridled race for the first truly functional quantum computer. A race that is probably accelerating research, but that can also have some undesirable consequences, such as splashy announcements based on flimsy evidence that does not stand the test of time. Point number two, the difficulty of the task that Microsoft has on its hands. It's not just a matter of developing topological qubits and using them to perform operations. It is terribly difficult to even check whether you have been successful or not. In fact, there is at least one other article about Majoranas written by other research group that had also to be retracted. I even talked about it at the time. So good for them, because they have bet big of an enormous challenge. Let's hope they will make it. And despite the difficulty, this is a very active field in which a lot of progress is being made, even if it can sometimes be undermined by all these controversies. For instance, do you remember the researcher who no longer works for Microsoft? At the moment, he and his team are working on another very interesting concept, the so-called poor man's Majoranas. The idea here is to simulate short Kitaev chains with just 2 or 3 sides using quantum dots. Although some of these systems lack topological protection, they could allow us to study some of the physics of Majorana zero modes in a system that is easier to control. Of course, getting topological qubits would be a big step forward. Time will tell whether we succeed in creating them and whether it's this or a different approach that will make quantum computers a reality. For now, I'd say an Italian scientist would surely smile to see how far his name has come a century later, although that's a story for another video. And remember, if you want more science, just hit the subscribe button. And thanks for watching.